Good evening, everyone. Welcome to the second interactive session of NPTEL GATE series. So today we'll be looking at the topics of friction and its applications and the plastic analysis of structures. So welcome to the second session. For the benefit of those who haven't attended the first session, let me announce this. So in order to access uh, the content that I'm sharing, the presentations, and if you have any doubts, you can ask here. So if there are new people who haven't attended the first session and uh, you wish to join this Google group, I am pasting the link in the chat window. So this will help you access the content that I'm sharing, and also you can post your queries. I'll clear it up in the next session. And you can also suggest the topics for the next session. So we'll have it interactive. So as I said, today we'll be looking at problems in friction and its applications and plastic analysis of structures. So before we get to it, let us have a quick recap of what we saw in the last week. So mainly we focused on rigid body statics. So we saw the basic concepts, the idea of scalar, vector, the various types of vectors. We saw fixed vectors, free vectors, and sliding vectors. And we also saw that the sliding vector follows directly from the principle of transmissibility. So you have a rigid body subjected to an external force. That force can be translated along its line of action without affecting any of its effects on the rigid body. So that is a sliding vector. Force applied onto a deformable body is a fixed vector. You're not allowed to slide it because if you slide it, the state of stress strain distributions varies. And you also have a free vector such as displacement, which doesn't depend on any point that is attached to it. So these are the types of scalars vectors we saw. And we saw the vector law of addition, which follows the parallelogram law of addition. Then we looked at force systems, moments, resultants, and we saw three different statements of static equilibrium. In one case, it was what are they? One is the summation of, in the case of 2D, so one is sigma fx equal to 0. The summation of forces in the y direction is equal to 0. And the summation of moments in the z direction about an arbitrarily chosen point in the plane is equal to 0. Alternatively, we can also state them as the summation of all forces in the about any axis, say x can be any direction, is equal to 0. And you can also say the moments about two different points in the z direction should be equal to 0, with the only condition that the line connecting AB is not perpendicular to the x-axis that we have chosen. The reason is, if not, these two will boil down to the same condition, which is redundant, which is not useful for solving problems. And the last condition and the last equivalent statement of static equilibrium is that the sum of moments about 3 points in the z direction is equal to 0. So you can have you can have a body, can have 3 points, and individually about each of those points you can have the net moment to be equal to 0. These are the conditions, necessary conditions of static equilibrium for a rigid body. And here this you should make sure that A, B, and C are not collinear. If not, again, you will get a dependent condition, which is not useful for solving problems. So depending on how the problem is posed, you can choose to use either the first form or the second form or the third form. All three are entirely equivalent. Then we looked at the resultants and the principle of moments, which states that any system of forces and moments acting on a rigid body, any system of external forces and moments acting on a rigid body can be expressed as an equivalent system of a single force, right? You have a lot of forces acting on a rigid body. You can always express it as an equivalent system consisting of a single force applied at a point and a moment about that point. So this is the resultant force R and the resultant moment M. The resultant moment M is nothing but the moment of sum of moments of the individual forces. That is the principle of moments. We also saw special cases, special configurations, structural configurations, which are 2 force and 3 force members, where a body, if it is subjected to body, in the first case, if it is subjected to just two forces, the necessary condition for this body to be in equilibrium is that the two forces have to be collinear. So if a body is subjected to just two forces, then a necessary condition is that the two forces have to be collinear. So the other force has to be.
Excuse me, sir. Your voice
Yes.
is too low, sir. Another thing is I cannot able to access the chart.
You're not able to access the chat. Okay, let me. What can I do? Are you able to access the Q&A? Q&A thing?
The option is not showing in. I'm currently using the Meet app in the mobile phone. The chat
Okay.
option is not showing in apps.
Okay, 1 minute. So are you able to see any notification right now? Otherwise, I just sent one message in Q&A.
Can you increase your voice, sir? I can able to hear the voice.
Oh.
Can anybody tell us? I am
Yes, is the voice better now?
Sir, your voice is fine, I think.
Okay. Maybe, yeah, maybe you have to increase the volume in mobile probably. And if you're not able to access the chat, I can tell you what you should type for the Google group in case. So you just go to this and you just search for this NPTEL hyphen CE, sorry, NPTEL hyphen gate, and you can just search in all groups and messages. Was it? Let me check. Yeah, you can search for this all groups and messages. NPTEL hyphen gate hyphen, and you just search for it. The first one that comes is that is the group. So you have this NPTEL gate C 2023 to 24 binary. You can join it. And chat window, I don't know why you're not able to access. I have provided access to everyone, but at least Q&A, I think you should be having. Yes, right?
It is going on loading. In question answer series, it is going on loading, sir.
Oh, okay, okay. Then I think it will come. No problem. It will probably load.
Okay, thank you, sir.
Yeah, yeah. Yeah, so I was talking about two force and three force members. So in case of if you have two forces acting on a body, then both of them should necessarily be collinear and equal in magnitude and opposite in direction. And if you have a three force member, if you have a body subjected to just three forces, then those three forces must necessarily be concurrent at a point. So they have to be concurrent at a point. Not only that, they should form a force triangle. So they should form a force triangle. They should form a closed polygon, which means the sum of forces is equal to 0. And if they're collinear, it means the moment is equal to 0. And we also solved two previous year gate problems. Then we also looked at undamped free vibrations of single degree of freedom dynamic systems. And we saw how the governing equation of motion is derived. And we also solved one problem from 2022 22 or 21 gate. So today, and if you have any questions from the last session, you're welcome to ask either now or towards the end of the session. So this is a recap of the last week. And as I already said, today also we'll have a problem which we aim to solve by the end of today's session. So this is a problem in plastic analysis of structures. You have a three-span continuous beam, so you can see it is statically indeterminate to the second degree. You have two intermediate supports which are not needed. So the redundancy of static indeterminacy is 2, and you have mid-span concentrated forces applied in the two spans. So the problem is as shown. So this load is increased up to the point where the beam collapses. So what is the minimum value of the load P at which the beam collapses? That is the question. So we'll look at the solution by the end of today's session. Before that, let us solve last week's problem of the day. So we were running short of time, so we couldn't solve this nice, interesting friction problem. So we'll solve this also today. And so let us get started with today's session. So topics we'll be looking at are friction problems and plastic analysis. So friction, it is being asked in the gate several times. And plastic analysis, I think there have been repeated questions. So I think there was one in 2008, then 2014 set 1 and 2014 set 2. And also in 2000, I think 22 set 2, there was a question. So we'll eventually be solving all these questions. In today's session, we'll solve this, this, and this. So this maybe we can look at in the next session. So what is friction? So friction is a force that opposes motion, and there are two types of frictions. One is so dry friction is the friction between two solid bodies. So you have, say, a block, and you have a surface, and you are applying some force to the block, and the surface is rough. In that case, there will be a resistance coming from the surface to oppose the motion of the block, and that is the friction force. That's dry friction. So this dry friction opposes either impending motion or actual motion. So impending motion is when the block has not actually started moving. It tries to move in a certain direction, but the friction is opposing. That is impending motion. Or it can also oppose the actual motion. So actual motion is when a block is already sliding at some velocity, subjected to some forces. So if it is sliding at a constant velocity or some velocity, subjected to some forces, there is always a friction force acting opposite to the applied force. So this you can call it as kinetic friction, and this you can call it as static friction. So this is the concept of dry friction. It is quite simple. Then how do we model dry friction? So we have something called the Coulomb friction model. From experiments, people have seen that the friction force between two surfaces varies as this. So suppose there is an applied normal force on the block. Let us call it N. And so by equilibrium, we can say if the block is doesn't have any weight, the normal force coming onto the surface will also be equal to N. If you just set sigma Fy equal to 0. So when you have any two contacting surfaces, you always have a normal force between them, and you have some friction force between them. So the normal force you can by the surface on the block, you can directly determine by setting sigma Fy equal to 0. So they should be equal to N. If you plot the variation of the frictional force or the force, and of course P should be equal to Fs. So if you plot the variation of P, the force needed to push as a function of the normal force, it varies as this. So not the normal force. You can call it as say how the friction force Fs or the friction force F varies with the applied force P. So Fs acts opposite to P up to a certain limit. It is equal to F. So this is at 45 degrees. Up to a certain limit, F is equal to the applied force P, and beyond that limit, it saturates. So this is called the limiting friction of that surface, the limiting frictional force of that surface. And Coulomb friction model is something that is proposed to relate the limiting friction to the normal force applied. So the simplest friction model is that the maximum friction force that can be supported by an interface is a constant factor, which is called the coefficient of static friction, times the normal force. So this is when the block is at rest. And if the block is moving, you have the coefficient of kinetic friction times the normal force. So this is all this, The idea, the idea is when the applied force is very small, the friction force is exactly equal to the applied force. So friction force is exactly equal to the applied force up to a certain limit. Once that limit is crossed, the block starts sliding. And at that limiting value, when the block starts sliding, the maximum friction force is given by a coefficient times the normal force onto that surface. So very simple. This you would have studied in high school. So this is when the block is static, and this is when the block is moving. And there is slipping, basically. This is slipping. So that's all it is. And when we solve problems in engineering mechanics involving friction, so there are three types of problems. One is the condition of impending motion is known. So we know that the motion is impending and there is no actual motion. For example, if you have a block and say this is a smooth wall or something, and this is some rough wall, rough floor. And suppose you have a block here and you push it with some force P. So there will be a certain friction that is coming here, and there will also be normal force coming from this. So in this case, and of course you can have forces in this direction, call them some vertical force, say Fy or whatever. So in this case, we know that there is friction and there is no sliding, so there is only impending motion. So when you know that it is not sliding, the block is not sliding, and the motion is impending, there is no slipping, you can solve for the friction forces just by static equilibrium. Why? Because you know that until the limiting value of friction is reached, the friction force is simply equal to the unbalanced horizontal force. So if you know that the block is not slipping, or if the interface is not slipping, you can directly solve the problem by static equilibrium. And if it is slipping, you just have to find out the normal force and multiply it by the coefficient of friction. So if it is slipping, so in this diagram, if you see, this region is no slip. So when the force is less than a certain value, there is no slipping. So when the force is less than, when P equal to F less than or equal to F max, then there is no slipping. And on the right hand side of this point, you have slipping. So this is usually falling, but usually in cooling friction model, this is assumed to be constant. So if it is slipping, then the friction is capped at the value of mu times the normal force. So if it is known, it is just the limiting value, which is mu times the normal force. And the difficult problems in friction are when we don't know what is actually happening. So we don't know whether it is impending motion or it is actual motion. In such problems, what we assume is you assume the motion is impending and there is no slip at any of the contact surfaces. Under that assumption, we can solve for all the unknown forces by enforcing static equilibrium. And after getting the solution, you check whether these frictional forces, right? When you have, so you solve for the forces by static equilibrium equations, then you check whether the obtained frictional forces are less than the limiting value or greater than the limiting value. So if all the friction forces in the problem are less than or equal to the limiting value, then our assumption is correct. So you can directly accept the answer. If not, if it says that the friction exceeded F max, that is not physically possible. So we have got an invalid assumption, which means there is actually slipping at some of the interfaces. So if this is the case, then you assume that slipping actually happens wherever this violation is happening. Then you redo the problem completely and check all the surfaces. So this has to be done iteratively until you get a correct solution. So this will become clearer when we solve this problem. So this was last week's problem on friction. So you're having this assembly of a wedge of an inclined plane and a ball or a cylinder, whatever you call it as. So we are asked to calculate the horizontal force P on the wedge necessary to initiate the movement of the 40 kg cylinder. The coefficient of static friction for both pairs of contacting surfaces. So what are the contacting surfaces? One is at A and the other is at B. So they have given that the static friction at A and the static friction at B, they are equal to 0.25. The weight of the cylinder is given. Now we are asked to determine the friction force at the point B. And there is a hint that you should carefully check your assumption of where slipping occurs. So let us approach this problem. So physically, before we write down any equation or draw the diagram, you see what can happen here. So if basically look at this and do this thought experiment of pushing it. So is it possible to move the ball without slipping happening at both the points? Is it possible? You can answer if you have a you have an idea, you can answer. So is it possible to move the ball either up or down without slipping at both points A and B? The answer is no. So no, because if 2 points are fixed, then this cannot. If you fix 1 point of a rigid body, it can rotate about that point. If you fix 2 points in a rigid body which are not along a straight line, it cannot move. So definitely slipping is happening either at point A or at B. But where it is happening, we don't know. So that is this. That is what the statement says. Check carefully your assumption of where slipping occurs. Fine. So so that is secondary. So as I said, the first step always is to identify the system. For problem solving in mechanics, the first step is to identify the system. What is our system? Our system is this cylinder plus the wedge. Now let us draw the free body diagram of the system. So first let us draw the free body diagram of the wedge. And let us draw the free body diagram of the cylinder. So the cylinder is easy. Let us start with the cylinder. There is weight acting on the cylinder. Let it be W. Okay. So this angle is given as 10 degrees. Let us initially take it as some theta. So let us take it as theta. And finally, when we solve the problem, we'll substitute it as 10 degrees. So this is theta. As I said, this is a slightly difficult problem, but it will help you understand a lot of concepts. It involves all the ideas: equilibrium, force systems, friction, and so on. So this angle is theta. So if this angle is theta, what is the angle with the vertical? So this is theta. This is theta. And if you complete it, this will be 90 minus theta. Yeah, this will also be theta, 10 degrees in this case. So the contact at this point is happening somewhere here. This is a cylinder. So this is also theta. And let us mark the forces in the horizontal and the vertical directions. So at every contact surface, we'll have forces. At this point, let us have a normal force at point A and a friction force at point A. Let me mark it this way. Friction force at point A. Here also we'll have a normal force at point B and a friction force at point B, but I can always resolve it along horizontal and vertical components. So let me call this as Bx and By. So I have just marked it equal and opposite, nothing much. Now on the wedge, you should mark equal and opposite forces, right? So By is upwards on the cylinder, which means it should be downwards on the wedge. And Bx is towards the right, so here it will be towards the left. And you also have the applied force P. Let me mark it in red color. Is that all? No, there is also the reaction from the ground. So these are frictionless rollers. You can see the wedge is supported by frictionless rollers. So there is reaction coming from the ground, which is, we don't know where it acts. So it is acting somewhere. And let us, so what is its magnitude equal to? Can you quickly look at the wedge and tell what will the normal force coming from the ground be equal to?
By, sir.
Yes, it will be By. Which means what is Bx? Just N4 sigma Fx equal to 0. So this is nothing but P.
Yes.
Now coming to the cylinder, what is Bx equal to? We already determined it is equal to P. Now set sigma Fx for the cylinder is equal to 0. What are the only horizontal forces on the cylinder? One is Bx, the other is Na. So what is Na equal to? Should be equal to Bx. But what is Bx already equal to? It is equal to P. So that's it. We have solved for all the horizontal forces in the problem. What is left is the vertical forces. Now before we, now let us get to the vertical forces. So this is what we have. Now we don't need to look at the wedge at all. We can solve only the cylinder. So we have a force P acting this side. We have a force P acting here. You have the weight of the body acting downwards here. You have some frictional force coming here. Let's call it F at the point. Is it A or B? A. And here there is some vertical force which is By. And this is along this line. And this angle is how much? It is 10 degrees. Let us call it theta initially. So this is some theta. So we have already, this is what we have. We have already determined all the horizontal forces. What is left? We have two unknowns, Fa and By. Let us find out what Fa and By are. How do we find out? And before that, so the resultant of P and By will act in some direction. Say it can be in some direction like this. So this is the resultant. This is the resultant acting. So let us call it R at the point B. And this resultant can be, this is the resultant RB. This resultant can be resolved along two directions. So you can have a normal component of the resultant and a frictional component of the resultant. So just a minute. Let me mark the resultant like this. So the resultant is something like this. And the normal to the surface is something like this. So this is the resultant. This is the normal to the surface. So this is the tangent to the surface. So the resultant has two components. This is RB. One component is normal to the surface and the other component is tangential to the surface. What is the tangential component? It is nothing but the friction force at point B. So this will be useful later on. Just have it in mind. So there are two ways we decompose the resultant. One is we have the resultant RB. In one case, we are looking at its horizontal component, which is P, and the vertical component, which is By. And in the other case, we are decomposing it along two. So in this case, it is global horizontal and vertical axis. Here you are finding its components along some local axis, where one of them is normal to the surface and the other is tangential to the surface. So simple. So in one case, it is normal force and friction force. In other case, it is horizontal force and vertical force. But both the vector sums are equal to the same force, which is RB. So that is the idea here. Now, what is the magnitude of FB? Now, if you draw the free body diagram of this, you have NB, P, W, you have FA and FP. So FA and FB and NB are unknown in this problem. Let us quickly take moments about the center of the ball. Why do you think I take moment about the center of the ball? So that I can directly ignore the unknowns. These forces, so W, NB, and P act through this point. So if I take moment about this point, these three are not going to contribute. So what are we left with? FB, what is the perpendicular distance it acts at? R. And FA acts at R. So FB creates a clockwise moment of FBR and FA creates a counterclockwise moment. So what are we left with? We are left with FA is equal to FB. So the friction force, if this ball has to be in equilibrium, the friction force at the point A is exactly the same as the friction force at the point B. So let us call this force as F. So just note this result. The friction force at the point A is equal to friction force at the point B is F. Coming back to the equilibrium of this ball. So quickly, let us establish the moment equilibrium of this ball about the. So horizontal is already established. So let us take moments about the center again. Let us call this point O. And this is the angle theta. This is R. So if you take moments about the point O, the z direction is equal to 0. What are the forces? W will not contribute. FA acts at R and it creates a counterclockwise movement. So minus FA is nothing but F R. And what about the vertical force here that acts at R sine theta? And it creates a counterclockwise movement. So again, minus dy R sine theta. And this P will not contribute because it is passing through the center. So this P creates a clockwise movement plus P R cos theta is equal to 0. So this is one equation. What is the other equation? You can set sigma Fy is equal to 0. So that means By is equal to the so this is the total vertical force By is equal to this downward force, which is the friction force at A plus the weight W. So these are the two equations. Now you just substitute in the first equation, By is equal to F plus W. What do we get? We get minus Fr minus Fr sine theta minus Wr sine theta plus PR cos theta equal to 0. By this we get F is equal to what do we get F as? We get F is equal to you can cancel out R everywhere. You get P cos theta plus W sine theta. Sorry, you get P cos theta minus W sine theta divided by 1 plus sine theta. So until now we have not used any condition of slipping. So this is the magnitude of the friction force, which is obtained only by static equilibrium. So that is the first step, right? If you don't know anything, you assume you just enforce static equilibrium. So the friction force at this point and at this point is nothing but P cos theta minus W sine theta divided by 1 plus sine theta. Let's proceed. So the next step is to find out at which point slipping will occur. So to see at which point slipping will occur, we have seen that the friction forces are equal, but slipping will first occur when the friction force exceeds the limiting value. So now we should see where slipping occurs. Where slipping occurs first. So where F less than F max, or rather where F equal to F max occurs. So F at A is equal to F at B always, but F max at A is not necessarily equal to F max at B. Right? Because this is nothing but mu times normal force at A. And this is mu times normal force at B. So if the limiting values, if this is smaller, then slipping will occur first at the point A. If this is smaller, then slipping will occur first at the point B. So let us analyze the problem further. Let us first find out what is the normal force at the point B. How do we find that? Normal force at the point B is, you can resolve these forces along the this direction. So the normal, so you have the horizontal force P, you have the vertical force By, and you have the normal force N at B. So what N at B is, it is, and this angle is theta. So the normal force at the point B is nothing but Vy cos theta plus P sin theta. And By we have already determined, so By is F plus W, and F we have already found as this. So what is By? By is F plus W, but F is P cos theta minus W sin theta. Write it here. By is F plus W, which is P cos theta minus W sin theta divided by 1 plus sin theta plus W. So you'll get W sin theta here, and W sin theta will get cancelled. So you'll simply get, it is W plus P cos theta by 1 plus sin theta. And what is NB? NB is nothing but By. This entire thing multiplied by cos theta plus p sine theta. So this is nothing but you'll get w cos theta plus p cos square theta plus this one p sine theta plus p sine square theta divided by 1 plus sine theta. Let us simplify this further. So how do you simplify this? You have p cos square theta plus p sine square theta. So what is it equal to?
P, sir.
P, yes. So you have the normal force at the point B is equal to, we have W cos theta plus P sine theta divided by 1 plus sine theta. Right? You can just see the expression here, W cos theta plus P coming from cos square plus sine square plus P sine theta by 1 plus sine theta. So from the first term, we can have just W cos theta by 1 plus sine theta plus P into 1 plus sine theta divided by 1 plus sine theta, which is nothing but P. So this is the normal force at the point B. And what is the normal force at the point A? What is the normal force at the point A? It is just P. Right? So the normal force at the point A is P, and the normal force at the point B is P plus some positive number. So cos theta, sin theta, everything is positive and theta is less than 90 degrees. So P plus some positive number, which means mu times NA. So NA is less than NB, which means mu times NA is less than mu times NB. They said the coefficient of friction is the same. So F max at A is less than F max at B. But F at A is, we already found by moment equilibrium that F at A should be exactly equal to F at B. So the first slipping will happen at A because here the condition is exceeded first. So this is the smaller value. So first slipping will occur here. So what should we do? We have to use the equation, the force, the friction force at A starts. So when slipping starts at A, the friction force reaches its maximum value. And what is that? It is mu times NA. And what is NA? It is mu times P. But what is the friction force at point A? We already determined it is P cos theta minus W sin theta by 1 plus sin theta. So just substitute the values. You get P cos theta minus W sin theta. So F is equal to P cos theta minus W sin theta by 1 plus sin theta is equal to mu times P. So that's all. We have an equation. So what is that we have to find out in this problem, right? You're asked to determine the horizontal force P. So you have one unknown in this equation. The only unknown in this equation. So left hand side is this, right hand side is this. So the only unknown in this equation is P, and everything else is known. Theta is given as 10 degrees. So just rearrange and solve the problem, right? So if you just take all these to the other side, you get mu into 1 plus sin theta minus cos theta times P is equal to minus W sin theta. So therefore, the P limiting value, the P at which the point A just starts slipping is W sin theta divided by cos theta minus, because there's a minus sign, minus mu times 1 plus sin theta. So that's all it is. We can just substitute mu is equal to 0.25. Theta is equal to 10 degrees. They said it's a 40 kg cylinder, so it is 40 kgs into 9.81 is the force. So substitute these values. You get the limiting value of P to be
699.
699. Really? Can you check it again? This is 40 into 9.81. This is sine 10 degrees. So the answer should be around, let me check. So in the denominator, you have cos 10 minus 0.25 times 1 plus sine 10 degrees. So the denominator is alone 0.69. And in the numerator, you have W sin theta. So W is 40 into 9.81 into sine theta is sine 10 degrees.
Sorry, sir, it's 98, 98.5.
Yes. So the correct answer is 98 point something 98 point whatever 98.5 kilonewtons. Sorry, newtons. So that is how you solve it. So this is the idea. You assume something. Initially, you assume static equilibrium, get all the relationships. So don't assume anything for the friction force in the beginning. That will get you to a wrong solution. Just assume it is some friction force Fa and some force Fb. Find all the relations between them using moment equilibrium and force equilibrium. Once you get the relationships, then you check where it is likely to slip. So in this case, we saw both the friction forces are equal and the maximum friction values are not equal. So you see where it is likely to slip. Then in that point, you assume it is slipping and then get the rest of the solution. So this is how we solve friction problems. Is that okay? You can ask if there are any doubts.
Okay.
Yes. Okay, so if there are no doubts, I can go to the next section today. Yeah, you can review this. You can, and there is also another part that is asked. So that is trivial. What is also determine the friction force at point B. So we already know that friction force at point B is nothing but the friction force at point A, which is mu P. So this 98.5 you multiply by 0.25, whatever it is, it will be around 24 point something, 4.6 newtons per volt. So that is simple. Once you get the force P, everything else is simple. So as I said, the next part for today is plastic analysis of structures. Why do we need? So the typical analysis you do in structural analysis is linear elastic analysis. So in your courses on structural analysis and also for GATE, usually you do a linear elastic analysis. Why do we need plastic analysis? Because we do a limit state design. So we do a limit state design where we can make use of the strength beyond the yield point in the ultimate limit state of collapse. So if you have any material, say steel, you initially have a linear elastic stage followed by some yielding and strain hardening. There is ultimate, then it fails. So for any material, you have the stress strain curve like this. So even when the material at this point, way beyond the yield stress, there is some residual strength. There is some strength left with the material. And making use of that strength actually economizes our design. It greatly helps our design. It makes the structures less costly. So that is one reason. And in indeterminate structures, it helps a lot in redistributing the internal moments and so on. So we can do an economical design of statically indeterminate structures. So elastic design of statically indeterminate structures is very conservative. So when you do plastic design, when you do plastic analysis, you allow for the moments to be redistributed between various members. We'll see how it happens. And the assumption is that the material is perfectly plastic. So if you see what underlies the plastic analysis of structures, suppose you take a simply supported beam like this. Simple, you just have a simply supported beam subjected to some midpoint loading P. So if you see how the beam is responding to continuously increasing P, first you will see that for a very small P, the relationship will be proportional. So initially, P will be proportional to the midspan deflection, say call it delta. Say suppose midspan deflection is delta. Initially, P will be proportional to delta when the material is still linear range, when the material is somewhere here. And if you take the cross section there, if you take the cross section here, the stress distribution, you know how it is, right? All of you would have studied. It will be linear. Compression on top, tension at the bottom, and this compressive stress, let it be less than the yield stress Fy. Okay. So when it is the stress is less than the yield stress, when it is less than the proportional limit, the response is linear. It is just proportional. As you increase the load further, the stress gradually reaches the yield stress. So here you will have the compression will be equal to minus Fy, tension will be equal to Fy, which is the yield stress. At some point, the stress in the extreme fibers of the beam will be equal to the yield stress. Beyond that, what will happen? Beyond that, the stress cannot exceed. So ideally, if you, this is the real material response. So when we idealize it as a perfectly plastic material, there is no hardening. So there is an elastic followed by a flat region, which is the plateau region. So when you idealize it as a perfectly elastic, perfectly plastic material, the stress here cannot exceed Fy. So what? But you're increasing the load, right? Still, if you further increase the load, how it happens is the adjacent fibers will also start yielding. So what happens is the yield will spread to some point in the depth. And the rest of it where the stress is still less than Fy will remain linear. So here the nonlinear response will start because the stress distribution in the cross section is no longer linear. It looks like a trapezium. And the stiffness is slightly reduced because the yielded regions have the regions of the beam where it has yielded that has zero stiffness, right? So here the strain can increase indefinitely without any increase in the stress. So the material has zero stiffness wherever you have yielded, and only this region will contribute to stiffness. So here the compression is equal to Fy, tensile stresses are equal to Fy. Only this region. So the stiffness, the region contributing to the stiffness will decrease, but the load can slightly increase. So the stiffness, the global response will start decreasing. So the stiffness of the beam will decrease. And at some point, what will happen is the entire cross section will be yielded. So everywhere above a certain axis, you have the compressive stress equal to minus Fy, and below that you have tensile stress as Fy. At this point, the entire cross section has yielded, and there is no material point where you can increase the stress beyond Fy. So at this point, the load cannot be increased any further. So it is just the load will the deformation will increase indefinitely at a constant force. So this load, we call it as the plastic collapse load, PPL. And the point at which the yielding starts, right? The first yield at the extreme fiber starts. So say this is 0.1, 0.2, 0.3, 0.4. Corresponding points in the stress strain curve are like this. So 0.1 is somewhere here, 0.2 is here, 0.3 is somewhere in the middle, 0.4 is here. So the load at which all the extreme fibers have yielded, that is Py. Now, this is what is happening at a section. So you can take a small element and integrate through the section and find the moment. So corresponding to, for this section, the moment resisted at this stage is nothing but the plastic moment MP. And the moment resisted at this stage is nothing but the elastic moment My. And as we can see, the plastic moment will be much greater than elastic moment because this is a triangle which is inside the so there is this extra contribution that is coming from the plastic part. So the plastic moment will be greater than My. And this ratio MP by My is called the shape factor of the cross section S. So these are just some standard things. Now let us get into how do we actually analyze such beams. What will happen beyond MP? So when the load, so if you have a beam, when the load exceeds PPL, the load P is greater than PPL, all the deformation is concentrated at this point because at this section, the moment is completely MP. So there is no resistance to rotation here. So it forms what is called a plastic hinge. So it is similar to a hinged connection. But a hinged connection supports zero moment, but a plastic hinge has already accumulated some moment of MP. So this is what we call as a plastic hinge. When the entire section has plastified, when all the fibers in the section has reached the yield stress, the stress cannot increase any further. So the moment is capped at a value of MP, which is called the plastic hinge. It can freely rotate at a constant moment MP. So that is the idea. We assume, so this is the key assumption with when we do plastic analysis of such structures. there are some conditions when we do plastic analysis. So what do we analyze for? We analyze for the plastic collapse load. What is the plastic collapse load? The load at which we cannot increase the load any further. So if you have the response like this, PPL is the plastic collapse load. This is the delta. You cannot increase the load any further. So if you try to increase the force a little bit, it will deform excessively. So at that time, the structure would have collapsed. So we do this analysis to determine the plastic collapse load of the structure. How do we do it? There are three fundamental conditions for collapse to happen. One is mechanism. What is a mechanism? We'll come to it. So the first condition is a mechanism. So basically, you can divide bodies into two types. So if you have a body, say have some connected body like this. Say it is all are pin connected joints. All are pin connected joints. And you apply some force. So this is a truss. Under an applied force, what it will do? It will deform and resist the applied force. If you increase the force slightly, it will deform a little bit and it will stop. It will not indefinitely deform. On the other hand, if you cut down the middle bar, and you apply some force like this, it will just collapse. This is a 4-bar mechanism. So all these are free to rotate. There is no resistance at all. You can see that the members will not deform. Members will not develop any stress. It will just rotate rigidly and translate rigidly and form a mechanism. So it basically accelerates. So a structure is something that does not accelerate, that resists the applied forces by deforming and generating certain internal forces. So applying some external forces, it will generate some reactions. Not only that, it will deform. So as a material deforms, it will get stressed, and the stress is a kind of internal force which counteracts the applied external force. So that is the definition of a structure. And a mechanism is something that just accelerates without developing any internal forces. So the key, so first thing, at the collapse, the structure becomes a mechanism. It cannot take up any force. So what is the load carrying capacity of this? Nothing. It is just zero. So that is what happens to a structure at its collapse load. Beyond the collapse load, it cannot take any incremental force. So that is the mechanism condition. The next condition is equilibrium. Equilibrium must always be satisfied. So beyond the collapse load, maybe equilibrium cannot be satisfied. If you increase the force beyond the collapse load, it will accelerate. But at the collapse load, it is still in equilibrium with the internal forces. So that is the second condition. Third is the yield condition. What does the yield condition say? The bending moment in any cross section is always less than or equal to the plastic collapse load. So these are the three important conditions for it cannot exceed, right? As I said, when the entire section has become plastic, the stress cannot increase. The cross section dimensions are the same. So the moment resisted by that section cannot increase any further. So that moment, the maximum value of the bending moment is MP. So these are the three fundamental conditions under which finding the plastic collapse load is allowed. So one is it should form a mechanism. Second is it should obey equilibrium. That is sigma fx, sigma fy, and sigma mz all are equal to 0 at all points in the structure. And it should also obey yield condition, that the moment cannot exceed. If moment exceeds, then it is not a correct solution. It is what we can think of. So based on this, there are some three theorems of plastic collapse. So when we do the analysis, if you obey condition 2 and 3, right? If you obey condition 2 and condition 3, so you take an arbitrary bending moment diagram. So all of you know what is a bending moment diagram. You have some structure like this. You assume an arbitrary bending moment diagram. So that bending moment diagram need not form a mechanism. So you have a bending moment diagram. Only requirements are it should be in equilibrium with the applied forces. So you know how to draw a bending moment diagram. You make a section, take force equilibrium, moment equilibrium. About that section, you get the unknown bending moment at that section. So that will obviously be in equilibrium with the applied forces. And not only that, this moment should nowhere exceed the yield moment MP. Under these two conditions, if you find out a collapse load, that collapse load will always be less than or equal to the actual plastic collapse load PPL. So this is the actual response, right? So this P static is always less than or equal to P plastic. So if this is the actual response, and you want some way to find out this PPL, but we don't. But because for complicated structures, it is not easy. In that case, instead of satisfying all the three, you satisfy only one or two of them. One is equilibrium, and the other is in this bending moment diagram. Nowhere it exceeds NP. In that case, you will get an estimate P static, which is always less than or equal to PPL. So it is a conservative estimate. So in this case, what we have not considered, we have not enforced the mechanism condition. That is, the structure has not become a mechanism. It can still have some more load carrying capacity. So that is the idea. It has not become a mechanism. It is not accelerating. It is not at the verge of collapse. That is the idea. It is not at the verge of collapse. It is well below. It has not yet formed a mechanism. It just obeys equilibrium, and the moment moment is nowhere beyond MP. So it is conservative. The other extreme condition is kinematic analysis. So this is kinematic analysis. This is also called the theorem number 2. Here we assume that the structure has already formed a mechanism. Say if you have a fixed beam and you subject it to a midpoint load. So how do you analyze this? You know the bending moment diagram will look something like this. You don't need to worry about the actual magnitudes in a plastic analysis. That is the key thing. So if this has to become a mechanism, how many plastic hinges it should form? So this is statically indeterminate to the what degree? If you say ignore the horizontal forces, all forces are vertical. So it is statically indeterminate to the second degree. So to form a mechanism, it has to form 3 plastic hinges. We don't know which will happen first. So it can. So as you increase the load, these two moments are equal. It can form. So with 2 plastic hinges, it will form a simply supported beam with some MP here. And a third plastic hinge has to be formed so that it can accelerate. So beyond this, if you apply any incremental load, it just accelerates, right? Just accelerates. So this is the other extreme. So this you can enforce equilibrium, but you're not ensuring that you're not looking at the internal forces at all. You just assume it has already formed a mechanism, and then you find out at what collapse load this mechanism is formed. So this estimate will always be greater than or equal to the actual plastic collapse load. So if you do using theorem 2, you will get what is called as a P kinematic, which is greater than or equal to the plastic collapse. So is that okay? So when we solve a problem, it will become simple. You will understand. The problems are actually simple, but the concept is a little involved. The problems are actually easier than the friction problem which we just solved. So this is called an upper bound theorem. So if you want to get, but this is not conservative. This is kind of unsafe. It's a bit unsafe, but economical, right? So you have to be careful when you use the kinematic assumption. Then you have the third theorem, which is nothing but if you satisfy all the 3 conditions here, at the verge of collapse, when the structure is at the verge of collapse, it forms a mechanism. The internal forces are in equilibrium with the external applied forces, and it also obeys the yield condition. That is, the moment is always less than or equal to NP at all points in the structure. So to analyze these structures, we use something called the principle of virtual work. What does the principle of virtual work state? So the principle of virtual work states that the applied among all the admissible configurations, say you have a structure, can be any structure, you can have a portal frame, whatever, and it is subjected to some forces. And it will take up some deformed configuration like this. So if you have a statically admissible system of external forces, what is statically admissible system of external forces? They satisfy equilibrium. And you have some deformed configuration, then the work done by the virtual work done by the, so you assume So this is some deformed configuration, right? The correct system of external forces obeys, which are in equilibrium, obeys this condition. So if you have, in this case, so let us consider you would have used it in structural analysis. So if you consider just a cantilever beam, just deflecting by delta. So after it has deflected, the work done by the external forces, right? So the virtual work done by the external forces, which is P times this whatever. So over and above this delta, you have some virtual displacement. Say let us call it V. The work done by the external forces P into V is equal to the internal forces. What are the internal forces? You have moment everywhere. So the sum of the moment into say d square w by dx square into dx from 0 to n. So this you would have used in structural analysis. It is actually simpler in plastic analysis. So basically all the work we do, all the virtual work we do on the body get into the strain energy of the body. So that is the idea. This is the idea of principle of virtual work. The work among all possible equilibrium configurations, the correct one, the correct system of external forces that obeys equilibrium is that in which the virtual work done by the external forces, the total virtual work done by the external forces is equal to the net virtual work done by the internal forces. So when we again if we solve, let us get to the problem solving. It will get simpler. So here this is a question asked in GATE 2014 set 1. So you're given a prop cantilever beam, right? You're given a prop cantilever beam. So, and one more thing. So if you want the proof of these theorems, you can refer any advanced book on plasticity. The proof is not, it involves some concepts. And when it comes to mechanisms, so there is one relationship. So the number of individual mechanisms, let us call it N. And the number of possible plastic hinges, let us call it H. And the static indeterminacy, let us call the degree of static indeterminacy as S. So the number of possible, number of independent mechanisms is given by H minus S. So this will be useful while solving problems. So if you see, if you want to see how it happens, so if you take a simply supported beam, you apply a midpoint load and you increase the load till the structure collapses. So how will it collapse? It will initially deform like this. The bending moment diagram is something like this. The maximum bending moment happens here, which is PL by 4. The maximum bending moment occurs at the middle of the beam. And that bending moment keeps increasing till the structure collapses. So that middle section, initially like this, at some point it becomes like this. And when it's fully plastified, it forms a plastic hinge at the middle. And once it forms a plastic hinge, it can no longer take any load. It will just indefinitely deform. So this is a mechanism. So in a simply supported beam, the degree of static indeterminacy is 0. It is statically determinate. The number of plastic hinges formed is 1. And what is N? N is equal to H minus S. So the only mechanism that is possible is as I have drawn. It is only 1. Now let us take a prop cantilever beam. So here, how will again, you don't need to get the exact bending moment diagram. You just get the qualitative bending moment diagram. So you know here bending moment has to be 0. And as you go away from this point, there is a positive moment. And as you go away, there is a negative moment here. So here you can form, so either this can reach yield moment first, or this can reach the plastic moment first. So you can have a plastic hinge here and you can have a plastic hinge here. So what are the possible mechanisms? The only mechanism possible is like this with the applied load. Now you check whether the formula works. The static indeterminacy is 1. The number of plastic hinges is 2. And how many mechanisms you are getting? You're getting 1. So the same goes to fixed beam. Right? You apply midspan force. So the bending moment diagram is something like this. It can form hinges here, here, and here. And what is the static indeterminacy? Like ignore the horizontal forces. So the degree of static indeterminacy is 2. The number of plastic hinges is 3. And the number of mechanism is only 1. So this is the only mechanism. On the other hand, if you take a continuous beam, like this and subject it to some forces. So how many plastic hinges it can form? Plastic. So the bending moment diagram will be here 0, here maximum, something like this. So it can form plastic hinges here, here, and here. So you can have plastic hinges like this. So the number of plastic hinges is this is not plastic hinge, this is a real hinge. So the number of plastic hinge is 3. The degree of static indeterminacy is just 1. And the number of mechanisms is 2. What are they? It can either form a mechanism like this, or it can form a mechanism like this. So this is one mechanism. The other mechanism is like this. So depending on which hinge will yield first, which section, either this will yield first, either these two will yield first, or these two will yield first. So in this case, these two, if they yield, this is the mechanism. And here, if these two yield first, this is the mechanism. So there are two mechanisms possible here. And the collapse load is given by the smaller load of the two mechanisms. So is that okay?
Sir, how can be the number of mechanisms and number of plastic hinges can be determined?
How the number of mechanisms can be determined? Okay. So the number of
As well as
mechanisms.
the plastic hinges.
Yeah.
As well as the number of plastic.
Yeah. So number of mechanisms, it comes with practice actually. So the number of mechanisms usually it comes with practice. So since we don't know that only, we have this formula. When we are just starting to learn, we don't know how to determine the number of mechanisms, right? So particularly for, say, if you have a portal frame, there are many mechanisms that are possible. So because it is something like this, right? Bending moment is something like this. It can hinge here, 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 here. So many are possible. So the number of mechanisms is usually not known. You need to identify all possible mechanisms. So that is a little bit difficult. But this can be determined. The number of plastic hinges that you can determine. How? I'll show you. So when you, let me go to the end. Yeah. So plastic hinges are most likely to occur wherever. So plastic hinges are likely to occur at maximum bending moment. That makes sense, right? So if you have a fixed beam, this is the bending moment diagram. So we don't need to know whether this is maximum or this is maximum, but anywhere compared to anywhere in between, it either occurs here or here. So plastic hinges can, at most you can have a plastic hinge here, here, and here. Once these three plastic hinges have formed, it cannot form anymore because it has already formed a mechanism. The moment cannot increase anywhere else. So that is how you determine the plastic hinges. So from a problem solving point of view, if you have a continuous beam like this, say many span continuous beam, and you have forces somewhere like this, just get a qualitative diagram, qualitative bending moment diagram. So here bending moment has to be 0, here some value, here some value, here some value, here it has to go to corresponding to this. Here again some other value, here some value, here you have. So this is how it is. So plastic hinge can form here, can form here, it 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 can form here. So in this case, the number of plastic hinges is 1, 2, 3, 4, 5, 6, 7. So wherever you have a sharp turn in the bending moment diagram, right? We don't know the relative magnitudes. Remember, we are just getting a qualitative bending moment diagram, looking at the loads. So here, wherever you have a sharp concentrated loads, you know that you can. It is possible that that has the maximum bending moment. Maximum bending moment can happen anywhere. So that is why we have this flexibility, right? Maximum bending moment can happen anywhere in the structure, but it can happen at one of these points. That is what we know. The maximum bending moment will happen at one of these points. Wherever it happens first, that mechanism will dominate. So in this case, you have these are all the possible points where you can have plastic hinges. So in this case, the number of plastic hinges is 7. And the degree of static indeterminacy is 1, 2, 3, 4. And the number of mechanisms will be 3. So what are the 3 mechanisms? Here it is just this, this, one at a time. So is that okay?
Yes, sir.
So you don't, yes, somebody else has a doubt. Okay, no. So you don't need to know the number of mechanisms beforehand. If you can identify the sharp points in the qualitative bending moment diagram, that will usually be the number of hinges. That's all. So maybe we don't, let us solve one problem and we'll have the rest for the next session. We'll just solve this. It will not take much time at all. It will take very small. It is, as I said, the concepts of plastic analysis are little involved. You need to know all these things. But when you solve problem, it is actually quite straightforward. So let us approach this problem systematically. Now this is a propped cantilever. So what is its static indeterminacy? Yes,
One,
it is
sir.
simple. 1.
1.
Yes. So find out the ultimate collapse load in terms of the plastic moment by kinematic approach. So they are asking us to use the second theorem. Mostly in GATE, you will be asked to use the second theorem only. Because first theorem means you need to get a bending moment diagram which is in equilibrium with the applied loads, which means you have to do an elastic analysis. But elastic analysis means that is the analysis of statically indeterminate structure. For that, you have to draw all the things, right? You have to get this primary structure, redundant structure, and all that will take time. So usually in GATE, you will get only the kinematic approach, which is simpler. So kinematic approach means you have to find the number of mechanisms. So first, so what is the number of plastic hinges? Let us look at it. So first, let us get the bending moment diagram here. Qualitative bending moment diagram. We don't need, if you are using the static approach, you need to get the exact bending moment diagram and enforce M less than My and analyze it further. That is difficult. Kinematic is easy. What is the qualitative bending moment diagram here? At the point Y, bending moment has to be 0 because it is a hinge. At this point, it will reach some maximum. And at the support, it will have some value. We don't need to know whether it is more at the support or at the applied load. So we know that plastic hinge can happen here or here. So plastic hinge is possible here and here. So the number of possible plastic hinges is 2. So the number of mechanisms is H minus S, which is 1. So the only possible mechanism is 1. Let us find out what it is. It is nothing but this. So at this point, it is free to rotate. And at this point, it is free to rotate. Now, finding the collapse load is just one step. Let us draw the structure at the verge of collapse. At the verge of collapse, so this is the initial configuration of the structure. Ignore the elastic. Again, this is an important assumption. Ignore the elastic deformation. Why? Usually for materials like steel, the elastic strain is something like 0.002. And the plastic strain is something like 15%. So this is like 0.15. So this is like more than 90 times the elastic strains. So you can safely ignore the elastic strains. Elastic strain is less than 1% of the plastic strain. So when the structure is at the verge of collapse, the mechanism that we have considered is there is a plastic hinge here. There is a plastic hinge that is formed at the middle of the span. And you have this roller here. And what are the forces that are acting? You have a force applied here. And this is P kinematic. You have assumed a mechanism. And what are the other parameters? So this is L by 2, L by 2. So this is L by 2, L by 2. And this has already formed a plastic hinge. So what will be the moment in the plastic hinge? What is the moment in the plastic hinge? I told, right? So this rotates downwards, so the moment will be hogging. Right? So when it forms a plastic hinge, this is a plastic hinge, right? The entire section has got yielded plastically, so it doesn't have any stiffness and it becomes a hinge. At this point, we call it as the plastic moment of resistance, MP. So if it has formed a hinge like this, the moment of resistance here, the bending moment, internal bending moment will be MP here and MP here. Suppose the load moves by delta, right? Suppose the load moves by some delta. What is the external virtual work? So external work done. The work done externally is, so there will be reactions here, but they are not causing, they are not doing any work. They are all they are fixed, right? They don't move vertically. The external virtual work done is P K times delta. And what is the internal virtual work done? Ignore. So leave all the work done by the internal moments, because here the rotation is very small compared to the rotation of a plastic hinge. So say this rotates by theta. How much is theta? Theta is equal to delta by L by 2. Here also, this delta is the same. This is L by 2. So this is also rotating by theta. But here there is no moment, so that will not do any work. Here there is a moment, MP, that will do a work of how much? MP and theta are in the same direction. So it will do a work of MP times theta. Here, this MP, so if there has not been a plastic hinge, the beam will be straight. And the beam has rotated by some angle. What is this angle? Can you check? Can you quickly tell what is this angle? This is theta. This is theta. So what is this angle? Exterior angle theorem for a triangle, right? This forms a triangle. So using the exterior
2 theta.
2 theta. So this plastic hinge is doing an internal work of MP times 2 theta. So just equate the two. Pk times delta is equal to MP plus MP, 2 MP is like 3 MP. And what is theta? Delta by L by 2. So delta by L to 2. So it is nothing but 6 MP delta by L. Just cancel delta on both sides. We get plastic collapse load as 6 MP by L. So it is option. Which option? C. So this is the procedure. So don't worry about the theorems too much. When you solve the problems, you don't need to worry about this too much. These are just telling, when you have a complicated structure, these are all useful. But in gate, mostly you will get simple frames, or say this is a prop cantilever beam. The next question is a overhanging beam. So in this case, you'll have two mechanisms and you have to take the minimum of the two. So this is also simple. So don't worry too much about what kind of mechanism can develop and those things. So this upper bound, lower bound is just a theorem. But for the structures that you usually solve, you will usually just get one or two mechanisms. And in that case, it is quite simple. You can analyze it geometrically. Wherever you have a plastic hinge, so let me write down the steps. So it will be helpful. Steps is, first step is to determine, so qualitatively draw the bending moment diagram. You don't need the numbers, just get the qualitative bending moment diagram. Then put a hinge at every sharp corner. Put a hinge at maximum bending moment. Wherever you have the maximum bending moment, wherever you have a sharp corner, you can put. So you put a hinge there and count the total number of hinges. Next step is static indeterminacy. What is static indeterminacy? You can find that out and then determine how many mechanisms you should consider. So the total number of mechanisms will be H minus S. Then for each mechanism, draw the deflected shape. So one more thing is there will be elastic deformation all here. So it will be slightly curved. But that doesn't matter because that is like less than 1% of the plastic deformation. So that is negligible. You only look at the plastic work done. So for each of them, draw the deflected shape, get the relation between the load point displacement delta and the rotation at plastic hinges theta, theta to theta, whatever. The last step is to, so the work done by internal moment, right? The work done by the internal moment, which is the plastic hinge. In this case, the plastic hinge acting on theta, sum of all such things is equal to external work done. Equate this, you will get, so external work done will have the collapse load P, internal work done will have the plastic moment of resistance MT. Equate both, you will get the collapse load. So that is very simple. So this is the idea. This you can apply to these problems. As we are out of time, we will take it up in the next session. Okay, so these are also simple. Don't worry much about it. So here you will have how many mechanisms? You'll have two mechanisms, right? This is statically determinate. The bending moment will look something like this. So you have two plastic hinges. S is 0. So N is 2. So we'll consider two mechanisms and solve this problem next time. And we'll also solve this problem next time. Yeah. Don't confuse too much with this. This is just there. This is just to say how the method works. So key thing is principle of virtual work. Draw a correct deform shape, and then you can equate the internal virtual work to external virtual work. You get the collapse load in one step. That's it. So let me pause here. If you have any questions, you're free to ask. Yes. Any doubts? Is it clear, the plastic part, plastic analysis part? Is that okay? Or if you want some portion to be explained again, I can. And the reference for this, right? The reference for this is where is it? Yeah. So you can go to this Instat teaching materials. I don't remember the expansion. So this is a wonderful resource for design of steel structures. So the entire, starting with basic design of steel structures into inelastic design and stiffener design, all of it is very nicely covered in this set of teaching materials. You can, as usual, I'll upload the presentation so you can check out this link. It is this one. So you can this one, InsDag steel design. You can go to this teaching material. You have everything chapter wise. So it starts with basic things like design of tension members and compression members, and it goes on up to steel bridges, multi-story buildings, earthquake resistance, bolted connections. So it has example problems. It has a theory, and it is free. You can access it for free. Only thing is you just have to give your name, mobile number, and email. Just submit it. You get the, yeah. So this is the kind of material they provide. So whatever I spoke about, you can get here. This elastic stresses in beam, plastic zone. This is what I just told, right? The mechanisms for a simply supported beam, prop cantilever. Yeah, and they also have beyond towards the end, it may be a bit advanced because they deal with plastic analysis of frames, gable frames, portal frames, and so on. But you can see this, it will be helpful. Virtual work, yeah, continuous beam. How do they see? So this is one collapse, this is the other mechanism, this is the other mechanism, and they get the collapse. So this will be very useful. You can go to this website and then click on whichever point you want to study. This is for entire steel structures. It is very good. The material is very good. You can go through this. Any other doubts? You can feel free. I think this time the interaction is a bit less compared to last time. Is it because it is tough or is it not clear? If you want, I can tell again. You can next session also. I can take it up. Portions that are not clear. How is it? Can you give any feedback? It is okay. Okay, fine. So, okay, so I think can we end the session? You're able to follow, right? I just want to confirm. If you're able to follow, then we can go at this pace.
Yes, sir.
Okay, so yes, that's all. So as I said, you can go through this slides again. I hope the friction part is clear. That is that equilibrium and some those things. And this is slightly advanced since it is not typically covered in BTech. It should be covered, but it is usually not. But since it is slightly advanced, it may take some time to sink in. But the problems, as I said, if you know how to solve it, it is very simple. The steps in the problem are very simple. You just have to find the critical points, assume there is a plastic hinge, draw the mechanism correctly, and once you draw the mechanism correctly, problem is almost solved. You should draw the mechanism correctly, find out how much it rotates. All hinges have MP only. There is no difference in that. All hinges have the moment of resistance MP only. You just do this internal work done is equal to external work done and solve the problem. That's all. So yes, so don't worry about it. It will be solvable. So
Sir, how the direction of MP is assumed at the both plastic hinges?
yes, I'll come to that. So how do we assume the direction of plastic hinge, right? So in this case, in a prop cantilever, when you draw the qualitative bending moment diagram, right? You know, here it is hogging, here it is sagging, here it is zero. So where you have a sagging moment, so what does it mean? What does it mean when you say the moment is sagging? So it means that it has a tendency to rotate the beam. If you take a small point here, if the moment is sagging, it means it will try to bend the beam like this. And if you say this is positive, this is negative. And when you say the moment is hogging here, say this is 0.1 and this is 0.2. At 0.1, the beam tends to go like this under the action of the plastic moment. And at 0.2, what happens? You have a hogging moment. So you usually mark it like this. So that will try to make the beam like this. So on this, on the small segment, MP is like this. As I said, you're fixing, right? So this side cannot rotate. So on this side, if you take a small, very small infinitesimal segment, it tries to rotate the beam like this. So here MP is like this, and the beam has also rotated like this. When you assume the mechanism, the beam is also rotating this way. So the direction of MP is determined only from the sign of the bending moment diagram. That has got nothing to do with the beam rotation or anything. So in the case of a propped cantilever where you have a hogging moment, mark MP like this. And where you have a sagging moment, mark MP like this. So this, if it is sagging, it is like this. And if it is hogging, it is like this. So if you say, for example, if you take a continuous beam, the qualitative bending moment diagram is something like this. Here it is hogging, sagging, hogging, sagging. So at this point, when you draw the plastic hinges, so here you can have a plastic hinge, here you can have a plastic hinge, here you can have a plastic hinge. So the mechanism is something, sorry. So how many plastic hinges? 3. Number of static indeterminacy is 1. So there are 2 mechanisms possible. So one mechanism is this. So here it is hogging. So how is the, sorry, sagging. So the bending moment is like this. Here it is hogging. So the bending moment is like this. This is one mechanism. and the other mechanism is like this here. Here you form a plastic edge, here you form a plastic edge. Again, here it is in the bending moment diagram, it is positive. So here you have MP like this. Here you have a bending moment diagram, it is negative. So here you will have MP like this. And the work done by MP is the rotation from the straight beam to the curved beam. So this is MP, this is MP. So if you extend this beam in the initial configuration, it was initially straight, then it is rotating by theta. And on this section of the beam, so look at the side where only where rotation is there. So on this section of the beam, MP and theta are in the same direction. So it is just MP multiplied by theta. Here you're assuming initially the beam is like this, and the beam has rotated by 2 theta. So on this section of the beam where rotation is happening, MP is in this direction, and theta is also in the same direction. So you have plus MP into 2 theta. That is how you determine the sign. So the individual signs of MP and theta, they matter, but what is more important is the product, whether it is doing positive internal work or negative internal work. So that is more important. So to answer your question, the direction of MP simply follows the qualitative bending moment diagram. Is it sagging or hogging? The direction of MP times theta depends on whether MP and the rotation are in the same direction. So it's like you hide this portion of the beam and you see only arm which is rotating. So in that case, MP is rotating by theta in the same direction. So the work done is positive. Don't put a minus sign here, because if you call this, because if you say this as theta, this is 2 theta is minus. So don't worry about the negative sign, negative sign of MP. So if it is hogging, the moment is negative. But what matters is MP times theta. So if theta is also negative and MP is also negative, it doesn't matter. Both are clockwise, so it doesn't matter. Is that answering your question?
Yes, sir. It is clear.
Yes. Any other doubts? Next time we'll take this problem. We can take up this problem, which is centroids, and we still didn't see how to actually find out the plastic moment, right? So to see that, we'll see this problem. So now we know if an MP is given, what is the load carrying capacity, we can find out. But what is MP, how to find out, that we'll take up in the next session. So others, if there are no doubts, maybe we can end the session. Thank you, Shaili, for claps. Yes. Okay, thank you, everyone.
Thank you, sir.
Let me end the session here. As usual, I will upload the relevant files and the video. Thank you.